Hi everyone, I'm Sam, one of Chris's PhD students. I'm going to be doing this lecture on specialised architectures for modelling sequential data such as text or audio that are variable length. We're going to be having a look at the kind of baseline historical approach known as recurrent neural networks and the problems that come with them, such as vanishing and exploding gradients, and the solutions such as long short-term memory, which are kind of similar to residual architectures, as well as the more recent approaches based on neural attention, such as transformers and the large-scale variants of these, such as OpenAI's GPT-3, as well as the approaches that kind of speed these attention-based methods up. So what is a recurrent neural network, or RNN? Well, at a high level, a recurrent neural network is just a function which is applied to nodes on a graph. And you can think about any piece of data as a graph. For instance, an image can be seen as a graph where each pixel is a node and the edges are a relationship between all of these pixels. What we like to think of, though, is the autoaggressive property where each node is only related to kind of the previous ones, and we create this ordering. The text this makes a lot of sense because each character can be seen as just a function of all the previous ones, and we're kind of same with audio. We only base our next one off the previous ones, and this isn't strictly true. We do choose our characters based on what we're going to say next, but this works quite well in many cases. But these functions in general can be applied to any graph. For instance, you can have a recursive neural network on a tree. So how can we actually model this data? Well, what we do is we have a hidden state vector, which acts as the network's memory, and when we take each input x, we update this hidden state h, and use that at the next step. So we have this cyclic property where we take a new input and we're updating the network's memory based on what it's seen, and it allows it to make more informed decisions based on the next character it sees, and then based on its outputs as well. So our standard neural networks we've seen are one-to-one, which are feed-forward, but recurrent neural networks allow a lot more variety in the number of inputs and outputs. For instance, one-to-many, which could be seen as image captioning. For instance, you have one image and we produce a sentence as an output, which is variable in length. Many-to-one, for instance, sentiment analysis, where we take a sentence and we just want to say whether it's happy or sad, 0-1, as well as many-to-many, such as neural translation, where we have one language to another language and this sentence is different in length. So we'll have a look at a simple implementation of this. What we tend to just do is just have our hidden state and we update that with a linear transformation, as well as a linear transformation of our input, add that together, and that will give us our new hidden state. And then feed that through another linear transformation and give us our output. And we can visually interpret this as a cell, which is just the same thing. We stack our hidden state and our input, multiply it by the weight matrix, apply non-linearity, and that gives us our new hidden state to repeat the process. So we use the same weights at every single step, and that gives us kind of a level of efficiency, which is quite nice. One thing we can do with our vanilla RNN is use it as a generative model, using that autoaggressive property. So the probability of getting a character in a sequence is only based on the characters that we've already seen. So in this example here, we have this word hello, and we want to predict the next character based on the ones we've seen. So we have this one hot encoded sequence of each character, and that produces our hidden state, which is updated and is a kind of a memory of what it's seen so far, and then it should calculate the probability of the next character. One thing you notice here is that each of our inputs aren't truly the output. We're using the true input characters, and this is known as teacher forcing. That is, we're using the training data at all input steps, and this significantly speeds up the training process, because if we're using the output, then the only information the network has is that first character predict the entire rest. But this has a problem because we're never actually going to produce the same sequences as output as with our training data, and this produces this compounding error. One solution to this is known as scheduled sampling, where we just with some probability use the output of the next step as the input. And of course at test time, if we want to make a new sequence, we just pick some random character to start with, or just a zero vector if we've started with that in our training. And then we take our output every step and pass it in the next step, and repeat and make a new sequence. And this works quite nicely, but to training it's naturally sequential, so it's quite slow. How do we train these? Well, it's very similar to just a normal neural network. This is called graph unrolling, where we just look at our hidden states one by one, and same with the inputs. Obviously, it's the same weights, but we just unroll it. We calculate the loss, and we just apply it back through the network, backpropagate through this unrolled graph, and these gradients accumulate additively in the weight matrix. Problem is, when we're training with sequences, they're all different lengths, and if we're lucky, we can get a batch where they're all the same length, and that produces it nicely. But in general, this isn't the case. We can get around this by just padding our inputs with zeros, and just ignoring the loss at certain points. Another problem, though, is that our sequence can be really long. For instance, if we want to train on the entire Wikipedia page, and we can run out of memory on our GPU. So what we tend to do in practice is shorten our sequence. We kind of batch it in smaller lengths, but we keep this hidden state connection, so it has knowledge of all the previous steps, but we only actually compute the loss during parts of the sequence rather than the whole sequence. Recurrent neural networks, however, have this huge problem which completely prevent them from functioning on even kind of smallish sequences, which is we have a look at just the gradient through a single step, where it's multiplied by the weight matrix W, and then we go through the next step and it's multiplied again by this weight matrix W, and then again and again. And if the weight matrix is small, then that product is going to converge down to zero, and obviously if it's going to get greater than 1, then it's going to explode exponentially. And this is a huge problem for training these networks. We can kind of see this explicitly down here in the kind of simplification of the backpropagation formula, which we can decompose into sums from each time step, how that affects this single partial derivative. And the key point here is this partial derivative here, from the hidden state at time t down to an earlier time step. It's this huge path through, and just this single partial derivative here, it's just kind of that's fine, that's normal. But the partial derivative from time step 4 down to time step 0 could be exponentially smaller or larger than that original one. So we have this sum here where some of the values are exponentially smaller or larger than others. If they're larger, then the training just completely is horrible and blows up. If it's small, then our long-term relationships just completely get lost, and we only actually care about the network can only actually learn about these short relationships. So basically, in practice, these standard recurrent neural networks can't learn long-term dependencies. When these gradients explode, though, there is quite a simple fix for it, known as clipping the gradients, where we just, if the gradients pass some magnitude, we just fix it to their maximum magnitude and just move that instead. And it sounds a bit hacky, but it makes a lot of sense if you think about it, because we don't actually, the whole gradient descent, we're kind of arbitrarily picking a learning rate that chooses how far we want to move, and we just say, well, just don't go too far, and then if we get some distance which is wrong, it doesn't really matter, we can carry on. And if we move rather than moving some huge distance away and have to make the way back slowly, we just move a much smaller distance and then we carry on with our learning, and it doesn't really affect it too much. So basically, when you're training recurrent neural networks, you just clip the gradients. You won't make the training worse, and it'll prevent these gradient explosions. But these vanishing gradients, when the weight matrix product converges down to 0, is a complete problem for these vanilla recurrent neural networks. However, we can get around this quite nicely with what's known as long short-term memory, or LSTM, and it's quite a complicated process, and most of this is completely unnecessary, or not unnecessary, but there are a number of other methods such as gated recurrent neural units, GRUs, which remove a lot of the complexity from LSTMs and perform similarly, maybe a little bit worse in some tasks, but these are kind of classic approach to fixing it, and it comes down to the same procedure really as residual networks, where we have two hidden states now, C and H, and on one of them, essentially, rather than multiplying it by the weights matrix at all, we just add to it instead, and this allows us this gradient path through, same as residual networks, where it just passes straight through, and that prevents our gradient vanishing or exploding. With that said, same as residual networks, when we have a lot of depth in a residual network, maybe like past 100 deep, or past a sequence length past 100, we're still going to suffer from exploding gradients. Just this trick is relatively nice, but it doesn't work that well. So when we're having a look at seriously long sentences, 2,000 characters in length, LSTMs don't work that well, and they don't learn long-term dependencies that well. But we have a look at what an LSTM does in general. They especially split it down to these gates, a forget gate, which looks at the hidden state and says, well, shall we forget it or not? And that's where the weights matrix is actually applied, but the network can learn, and basically the network learns whether to vanish gradients or not, because in some cases it's actually quite helpful to forget. Otherwise you have to remember all the information you've got so far, which is painful, and sometimes it's quite beneficial to not do that. Another really helpful gate is the gate, which is a horrible name, but basically the gate is where it really kicks off. That's the what's added to the hidden state, and that's effectively the new information that's added to it. And all of these gates have sigmoids on them, except from the gate, which has a tan H nonlinearity. So it's -1 or 1, and this is really helpful for a number of applications. So for instance, you're training an LSTM to generate code or sentences, and it can add 1 when it detects a bracket, for instance, and it can take away 1 when it closes a bracket. So it always has this counter of how in depth the brackets are. And you can decide, it's got too long, and it forgets it. Same, for instance, sentence length, you can kind of add a bit of number to it, and then sentence is getting a bit too long, it should probably go on to the next line. So it gets a bit high, and the forget gate kicks in and goes, right, time to make a new line, forgets where it was, and it starts again. It adds a new line, forgets it all, starts again. And that's kind of really why LSTMs work so well. It's just this path straight through, this gradient highway basically, which allows it to flow right through and additively forming this weights matrix, but they're all similar weights because it's additively rather than this huge product. And before I go and knock LSTMs too badly, they're actually not too bad, and they've been used for quite a few cool things, such as image captioning, when the sentences aren't too long, and you can see this cool application here where it's been trained on Shakespeare, and at first glance it looks like Shakespeare, but when you look even slightly into it, it makes completely nonsensical. I don't think it's chooses the same character twice, but there's some cool examples like that on this blog here by Andrei Karpathy. Also, LSTMs have been used for quite a few things recently, recently in the last few years, such as text-to-speech, and you can kind of get around that sequence length fixed 100 characters, say, by running multiple LSTMs running at different rates. So the first one looks at every single character, then the next one looks at every 4 characters, and the next one every 4 characters of that. So you have this huge growth in the number of characters that it can see. To talk about LSTMs really, sure, in theoretically they can store arbitrary old information. That's the same with normal recurrent neural networks, but practically they really struggle to store long-term information. They're really quite slow to train because they're naturally sequential. We have to compute the hidden state to then compute the next hidden state, and so on. And another big problem, which we'll kind of come to discuss, is that they're limited by that single hidden state has to encode all the information about the input. If we're doing something like translation, then we have to encode an entire input sequence into a single hidden state, get all that information into one single vector, which for a long sentence is a real struggle, and it kind of really breaks down in those use cases. One method that's been replacing standard RNN and LSTM methods is the idea of neural attention, where instead of encoding all the information in this single vector, we can instead look anywhere in the sequence we want to and directly access the information at that position. And that removes that hidden state bottleneck. And rather than having this path length of going through 1,000 sequence length to access an earlier character, we can just go, oh yeah, I want to look at that character 1,000 characters ago, and directly access it, which is really helpful. Say we have this sentence, the cat likes fish, it also likes chicken, then we need to know what's it referring to, and in this case obviously the cat is quite close to it, but in a much longer sequence, say we want to know what the title of the article we're looking at is, we might need to look quite a long ago to actually remember what the sentence is, the title is. So how does this work? Say we have this input sentence. Let's go. The cat is very happy, and we want to, say we want to convert this to French. We have this other sentence up here. It's a different length. So beforehand, we had to convert it into this single vector here, and we'd compress it using all this information here to then go into all the others. And that single vector has to encode all this information, and for a long sentence, that just doesn't work. So instead, one of the earlier attention methods was known as location-based attention, where we say, oh, I want to look at this somewhere between the second and third character. That's quite important to me. Say this character wants to look there, then it kind of produces this distribution over these few characters, and sums up the vectors weighted by this distribution. And that gives you a location-based approach that's differentiable, and lets you know. But this works quite nicely for translation or text-to-speech, where it's naturally an increasing step where if we're translating to French, the order is roughly the same as English, and if we're doing text-to-speech, then it's basically directly correlated. But more in general, we have some really long sentence, Wikipedia article, and I want to look 1,000 characters ago, but we have no idea what's there. So a much more recent, better attempt is known as dot product attention, and this is what transformers use. So instead, we have all these input vectors of sequence, and we'll call them the values because they're the actual content of the sequence, values v. And then we also have this sequence of vectors which we produce for each of our input, known as the keys, k. And these basically, rather than code the content of it, they say what it is. So for instance, happy, that's an adjective, and that's what these vectors describe, kind of the content of the vector rather than the description of the vector rather than the content of it. So this is now, we have this description of all of them, we have the content of it, and now we want to produce, to kind of directly access some area. And say here we want to go, I want to look at all the adjectives. So here we go, what's the similarity between this vector that I want and all of the previous ones? And in this case, we go, this is pretty similar, and actually this is pretty similar. And all these other ones, they're a bit less similar. And we add them all up based on their similarity, and that produces this new vector as the output, which is kind of a content-based way of addressing locations in the sequence. And see this explicitly here, where we look at all our inputs and we calculate this similarity function here, and then we just add them all up. And the similarity function that we use is a cosine similarity, so it's just the dot product between the queries and the keys, and then we normalize it and do a softmax over it to get something which adds to 1. And then when we multiply this softmax, then that's just this addition here. So what can we do with this? Well, one of the kind of common things we've spoken about throughout is translation, and this is the original attention is all you need paper where transformers come from. This is what they proposed, this architecture, and it's split into this encoder and decoder architecture. So the encoder looks at the inputs and it just extracts all of the information. It looks wherever it wants. It looks at what's beforehand, it looks what's later in the sequence, and it produces this encoding which describes what's in the sequence. And that's just attention layers and a feed forward at the end, but it's just encodes it, extracts all of the information, looks globally wherever it wants. And then this decoder network is what's a bit more interesting. So we have this multi-head attention, which is masked, just here. So that's basically saying it's causal attention, whereas autoaggressively with an RNN, it's automatically causal because it can only look at what it's seen before. Whereas now with our attention, we only want to look at what's in the past. So we have to explicitly mask the attention matrix and say, you can only look at what's beforehand. You can't look at what's in the future. So it looks at what is seen already, and then it also looks at these encodings. It looks at the input sequence, and then repeats this n times, and that's what produces our output sequence. And see this translation example here, which is actually not from a transformer, but this is exactly the kind of attention matrix that you get, where kind of roughly diagonal in this case because each word's corresponding, and this word's flipped around. So it kind of aligns quite nicely. And what's great about these transformers is that this attention mechanism is fully parallel. It's just matrix multiplications. So it's so much faster than long sequences on recurrent neural networks because we can do the entire thing in parallel. The problem with this parallelness is that we don't know where in the sequence we are. When we said, no, it's great, we can content based address things, but for some things we do want to know location based. I want to look what's the character before me, or I want to look 5 characters before, and we can't do that when it's all in parallel because it has no real access to location. And what they propose is this positional encoding, which you can see here is a kind of a sinusoidal encoding, and we just add this to the input, and this provides location information for all of our inputs and allows the network to then go, I want something that looks like this, and well, this is our content. So what you actually find with our input embeddings, which is kind of a description of the input encoding, so a character each has an encoding, they're learned, so they just ignore some of the parts of the vector and allow some of that information to be location based. Another example that's quite nice is the end-to-end object detection. So I believe if you're doing the computer vision module, I think you probably do end-to-end object detection. That's you find bounding boxes on the image for objects in it, and you also do the class. And one of the best methods, I think I got taught it was faster RNN, and it's a really complicated system with all these different components. And one of these new methods coming along, this year, is the DETR, which is a kind of transformer based, which has so much simpler architecture. And I think it's quite nice to understand, and it works quite nicely as well. So to start with, we want to extract features from the image, and then we have a convolutional neural network to just do that. So we won't bother with the size of the image really, we just want to extract some features from it. And then we flatten that all down, so each pixel in the image is now a vector, and it's now flattened that into a sequence. And it's the same just encoder-decoder architecture that we're using for translation. The encoder just extracts all the information from the image, and what's really great here, the transformer, it can look globally in the image. So we have some really big bounding box. A convolutional neural network can't look very far in the image, it doesn't have a big receptive field, whereas with this transformer attention-based architecture, it can easily look the whole length of the image, it's no problem. So we have this encoding now, and the decoder, well, it's a bit different. Rather than auto-aggressively predicting the next character in the sequence, we have these object queries, and these are just vectors that are learnt with the network, and they ask questions like, is there anything in the bottom left of the image that's quite big, or is there anything in the top left that's small? And that's just one vector for each thing. And so it starts off like this, and then they just do the same things before. They look at the encoding of the image, and they based on, I now want something that's in the left, it's asked for something in the left, top left, and then it goes, well, this is a bit interesting, maybe I'll have a look further, or maybe it'll go, no, this isn't interesting for me, and it ignores it, and it adjusts its questions until at the end it predicts, is there something in that location, or is there not, and it'll output bounding boxes and class locations. and has this relatively simple architecture compared to others, and works quite nicely. The attention mechanism is a bit slower than others because it's has to attend over the entire space, so you have these n squared connections, one from each pixel to every other pixel, but it's quite a simple architecture and it works quite nicely. Another great thing is not only can you get these bounding boxes, but you can also get segmentation maps, because the encoding all these attention maps encode a lot of information about the image, and we can just pass that through another CNN and use that to get segmentation maps instead. So that's a lot simpler than other methods. Another cool example is unsupervised translation, and this is kind of similar to your cycle GAN, except on variable length inputs, and this only works with inputs and outputs that are kind of share a lot of similarity. Basically, if you think of here we're doing Python code to C++ code or something, but it returns the same keyword greater than if we share a lot of max is all the same word. We share a lot of similarity. So essentially what you do is you use exactly the same encoder for both the different languages, and you encode that to a common space. So you tell the encoder absolutely nothing about what language the input is, and because the keywords are the same, it maps these words to similar spaces. And then the output, the decoder architecture, this is again just a standard encoder-decoder architecture. You tell the decoder what language you want to reproduce, and because you've encoded it to this common space, you can encode C code and then tell it to reproduce Python code, and it will do it. And they do a few different tricks, such as corrupting the inputs to kind of really encourage it to go to the same space, and also back translation, which is going on at the top. So they convert Python code, encode Python code, reconstruct C++ code, then encode the C++ code and reconstruct it as Python, and you can compute the loss between what we get out and what we had at the start, and it's called that that cycle consistency loss, which is kind of similar. And we can see whether it works by looking at the feature space of characters, and they do actually point to quite similar spaces, so it's quite a cool different method, but it only works because the languages are quite similar. If you think something like English to Chinese translation, you've got no chance. So the next thing we'll have a look at is GPT-3, which I'm guessing many of you know about already. Essentially the idea is just take our normal transformer model, autoaggressive transformer model, and make it big. And for the last kind of couple of years, it's been a real battle between OpenAI, Microsoft, it might be a third party, I forget, it might have been Google, kind of just pushing the models bigger and bigger and bigger. And this is the latest attempt in the arms race. This is what we hear: 175 billion parameters. I don't know how many GPUs that would be. 96 layers, 96 heads, tons of neurons, and interestingly, huge batch sizes, 3.2 million batch sizes. That must be a lot of where it's coming from. The training process. They have really small learning rates, but huge batch sizes. And interestingly as well, input lengths of only 2048, not that big, and that kind of explains why they don't actually do that well on really long sequences. That is a kind of a problem with these transformer models. Is with a normal recurrent neural network, when you train it through truncated backpropagation, you can still use the hidden state from a previous step, but because the transformer is completely parallel, if you want to truncate it, you can't look at the previous input steps. It doesn't really work. So what some of these methods do are look at just some of the earlier steps, not too much, not the whole sequence, but you can look at some of the previous steps, and because it's not only looking at all the previous steps, it's looking at the hidden states, the next layers of them. You're still getting this kind of high-level representations being passed through, but that still kind of really prevents these models from getting really long, just because the memory scales quadratically. The sequences can't get very long, but then these models still do pretty well. So read what you will, but they train it on huge dumps from the internet, petabytes of data, and it just basically showed they can do everything just from training unsupervised on the internet. And they demonstrate on quite a few tasks: few-shot translation, reading comprehension, that's like question and answering, give it a text and what's some questions about that text, as well as close book, so just given no information, who is Roy Patterson, something, and it just has to remember that. And it's actually, because there's so many parameters, it's really good at this sparse information. If you ask it, what's the capital of Finland, it'll remember that. What's the population of Finland, it knows that too. It has these groups of neurons that basically just act as memories, and it is quite similar to in idea anyway how our brains work. And also they say that it can reason, look at arithmetic, it can add, but there's certainly a debate to be had there. And I'll let you read that article if you want. I think that's a kind of cherry pick. That's the best article. People couldn't really recognise that, whether it was GPT-3 or a human, but overall it's pretty good. So you kind of really need to analyse, why is this model good? Is it good really? And the kind of the graph on the top right is quite interesting. So we compare it against some of the smaller models, but still looking at billions of parameters. It'd be state of the art for last year. And when you go to these huge models, they're really good at few-shot learning. So that's we basically say, please translate from English to French. But rather than just saying translate from English to French, we give it some examples. Here's a sentence and this is a translation. Here's another sentence, here's translation. And the more samples we give it, kind of better it is. And I think if that's kind of, it kind of extracts the information from what you've given it and looks for kind of corresponding websites that it's seeing corresponding information, and that's where it really does well with few-shot learning. Zero shot, you just say translate English to French, 10% accuracy. It's if you give it a few examples, 60%. It's it does a lot better. Even just one shot, you give it an example, it knows what it's doing. Just telling it what to do, it needs those examples. It's really good at few-shot learning, and actually in sometimes better than just models fine-tuned to do that, much smaller fine-tuned models. But as you kind of said, over long sequences, it's still not very good. Only 2,000 sequence length, it can't do well, and struggles with common sense physics. So ask it, does cheese melt in the fridge? It's probably going to say yes. It really struggles with those sorts of things. And then real problems that we need to discuss when we're kind of improving these models is the bias. We're training it on the internet, and the internet's full of bias, and they do some tests here of kind of sentiment analysis across different races or descriptive words across gender, and it's just inherently biased. Chris has been doing some work with another PhD student of few shot it, give it an example of some unbiased text, and then give it the task afterwards, and I think it's less biased. But there needs to be more research and really fix this bias problem before just rolling it out as they are on the internet for everyone to use, and it's a huge problem. And you think we're getting to a stage where, similar to GANs, where it's getting quite lifelike, but these are kind of artifacts that are a bit harder to spot, and huge model, at the end of the day, it reaches the point where you can't really distinguish it from human text anymore, and you have online bots all over the internet with huge numbers of them powered by GPT-3 or anything, fake news articles indistinguishable from humans. But there's many good things you can think of, there's bad ideas as well, so it's a struggle. But that's what you can do if you're Google, if you're OpenAI, Facebook, Microsoft. But how can we train these big models? And there's been a lot of research, I think these are mainly all from this year really, on how to make these models much more efficient. And there's been a strive for linear transformers, so rather than have this attention matrix where everything looks at every other image, can we somehow simplify? We still want to be able to look at everything, but rather than have to compute this n-squared attention matrix, can we make it simpler, bigger n? And there's just a few of the efficient transformers how they've been doing this year. And as a kind of motivating factor, we have a look at these graphs on the right are layers on the y-axis and the number of heads. So that's multiple attention mechanisms running in parallel on the x-axis. And as blue gets to red, these red colours mean that rather than just looking at one single position, we're actually looking at around 400 different input sequences. And these are on sequences that are around 512 in length. So that's almost looking at the entire input sequence at once. And that's just averaging. So we can simplify these models by just replacing some of them with averaging and save loads of memory, loads of computation by just doing some averaging instead. So you see the bulk of the work by this network seems to be done in those middle layers where it really picks out. So you're looking at 1, 2, 3, 4 different inputs and really selectively choosing what it wants to look at rather than just getting give me everything. So let's have a look at one of the newest methods of linearizing these transformers. So we run in big O of n time rather than n squared, and the same with memory. And the basic idea is first we can divide up our attention function here. So this is our normal transformer dot product attention function, but we would just rather than using matrix multiplications, just make them sums instead. So this top and bottom thing. It's just the definition of softmax when the similarity function is this with the cosine similarity in the middle. So obviously, we've got our normalizing constant, which is the sum of them all, and this is just the sum but multiplied by each component in the softmax. And we say, well, this similarity function is kind of an arbitrary similarity function, but it's kind of really restricting because we have to compute this every single step, can compare it against everything else. And you say, well, can't we use anything else? And you say, well, how about we use a kernel method? And kernel methods are kind of your traditional machine learning methods where you want to be able to map a function into higher dimensional space to be able to classify, draw a straight line to be able to separate it, similar to what the support vector machines use. But in that case, we use a kernel to approximate this high dimensional space without actually having to compute the high dimensional space. Whereas in this case, we just go, sure, we'll use this high dimensional space. We don't really care. So we use this new similarity function where we just map it using the phi function into a higher dimensional space and use this as our similarity function instead. And because these are now just the matrix multiplication, just the dot products, we can just drag this out, and now we just have this sum here, which is exactly the same thing for every single time step, and we can just pre-compute this sum for the top and the bottom separately, in big O n time, and then we can just do more multiplications at next steps, and that's the whole thing is just big O n rather than n squared, and that's great. But is this kernel function similarity, is it actually as good as softmax? And they show for a few different methods. I think they use an elu and a relu, and show it's not as good, but it's not bad, and it's pretty fast. But can we approximate softmax if we go high enough dimensions? And we can only approximate softmax exactly in infinite dimensions. However, we can approximate the softmax by approximating it Monte Carlo wise, and have some complicated approximation here with sampling from normal distributions. But we can do transformers in linear time with softmaxes by approximating it 32 times longer sequences on current GPUs. That's huge. So expect GPT-4 with huge sequence lengths, everything bigger, trillion parameters, everything bigger very soon, because these are where it's going, and I'm sure there'll be something better later, but it's a pretty cool trick and it's quite nice. And another cool thing that we can do from this is that this is the same kind of function from before, but usually we think of RNNs and transformers as these very different methods, because a transformer, it looks at all the inputs, but it doesn't have a hidden state. It's all done in parallel. There are no hidden states. So how can it be an RNN? And until now, there hasn't really been that unification. But using this kind of kernel method, suddenly it becomes incredibly clear, because this sum here and this sum, we can just kind of deal with them as cumulative sums instead. So this S is just this top sum, and Z is this bottom sum, and these are our hidden states. And then this fraction here is the value, is the new values. It is our attention method, and we just have some output non-linearity, linear function, residual connection, and a transformer is an RNN using this kernel form, provided it's done auto-regressively. So rather than looking over the entire input space, we only look at the previous ones, which is what RNNs are limited to anyway. So it's pretty cool, and we can see some samples here. These are actually from the not the softmax version, and I don't know about you, but they look pretty bad to me. They don't look that good, and I think that it's probably because using a different nonlinearity, the ELU or ReLU rather than this softmax approximation, isn't great for images, but numerically they work pretty well, and for sequences they seem to work pretty well. And I wouldn't be surprised if this new softmax version approximation works pretty decent with images too. But obviously be aware, with this approximating the softmax and doing it this way adds more complexity, and it only really gets the improves results time-wise for really long sequences. We're going over like a few 100,000 or something long, maybe over 1,000. So it's just like a 32 by 32 black and white image. You're kind of borderline whether you're getting any improvement from it. But for huge thousands and thousands of sequence lengths, these are way better. Another thing which is a quite interesting interpretation is Hopfield networks. So what's a Hopfield network? They're pretty similar to Boltzmann machines, so they're energy models and they're on binary units. But a Hopfield network is a recurrent neural network, but it's not like the recurrent neural networks we've seen so far. This is kind of the earliest recurrent neural network, and it's not a function approximator. It's just a storage method, basically. It's a fully connected graph, but the weights of that graph are all predetermined by the input sequences we want to train on. And essentially, rather than kind of learning a function, we just say, well, we have this new data point, and I want you to find me whatever your training sample was the nearest to it. And we do that by just minimizing this energy function. And actually, we can minimize that basically in one step. It converges exponentially, but one step's pretty good in this binary state. Another cool thing is that we can actually store an exponential number of patterns in these Hopfield networks with increasing number of neurons. And basically people have shown that transformers are actually equivalent to this interpretation when it's generalized to continuous vectors rather than these binary states. When the training patterns, rather than being training patterns, they're the keys and values of the transformer network. And this is pretty cool because transformers can store, we know now they can store exponentially many patterns as well. And we have a few different applications for them as well. Like currently with transformers, we access this distribution over all the inputs. We want to find all the things that are similar. But we can basically say, well, if we minimize the energy function in multiple steps, rather than just that single one, we can really get we converge on a single input and really focus on it. So we have a new kind of parameter we can play with as well, like controlling that rate of convergence, which is kind of natural to Hopfield networks. And we can really focus on inputs rather than getting this distribution. And show that they can also implement all these other layers as well, like pooling, like mean, which kind of is naturally thrown out of transformers anyway. Takeaway points. As you can have seen, LSTMs, they're not bad, but they're not what people are going for at the minute. If you have a smaller sequence, 100 characters long or so forth, then LSTMs are fine. But if you want the longer sequences, you have to go for transformers because they reduce that path length down to 1 rather than n across the sequence. The hidden state isn't a problem anymore. We can just completely flow through, and really great. But transformers are slow as well. We have to compute with n squared attention matrix, which is really slow, but new methods are improving that too. And we have all these cool applications which are using these encoder-decoder models, and for these smaller networks it's fine, but then you have OpenAI, Facebook, which are making these huge models, and they go, don't bother with these complex architectures, just train a huge model auto-aggressively on everything just to approximate the data, and that can do everything for you basically as well. Make a bigger model that'll do even better. That's pretty cool. So if we put all of the stuff we've learnt all together now, one thing we can do is give our huge auto-aggressive language model a short sentence introduction and get it to complete it for us. So that's what I've done on the right here, the deep learning module at Durham University. And we can also get another auto-aggressive sequence model to take this text and turn it into speech. And doing that, this is what we get.
The deep learning module at Durham University includes a new neural net called Lilliput, the most advanced model yet. It uses deep learning for its classification and recommendation capabilities. It has been used in more than 5,000 online articles to discover topics related to medical education, public health, and economics. If you are interested in the technical details of how this neural net works and what it can do, you should check out the accompanying blog post. https://blog.durham.ac.uk/deeplearninglilliputblog.
Yeah, which is not bad at all. Kind of linking Durham all the way to the start, it's making quite a realistic URL. I mean, the whole thing, it could be written by a person really. It's very not bad at all. This was done with Hugging Face transformers, which is actually a PyTorch library with lots of different transformers, like BERT is one, and I think there's quite a few big ones are all open so you can use. But they also have these pre-trained models available online. This one was GPT-2, sorry, so it's a little bit old. But I think there's a GPT-3 one out as well now where you can give it a go. It's not bad. Before finishing off here, we'll just have a quick look at the code linked in the slides. This one's having a look at translation with transformers. So how we're doing this is we're defining our source and target data. So this is a tokenizer, which is spacey. So this is taking words in different languages, English and German, and splitting them into different word tokens. So we're using this data set, multi-30, with the German and English translations, and passing in this to say split it into English and German and different tokenizers. So usually sometimes when you're training these models, there's the debate of what to split into each vector to define. So we've kind of been looking so far where each vector defines a character, and the huge auto-aggressive models usually work like this as well. But in this case, we're actually defining each vector to be a word, and we're assigning that a vector to each word. But if we assign a vector to every single word, then some of them are really sparse and won't have much information. So why do we do this rather than just assigning letters to a vector? Mainly just in terms of training speed, really. It's just a lot faster in this simple example to do that. But obviously you have the problem if you can't generate new words. So if we want to translate something with some weird word that it hasn't seen before, it unfortunately just can't translate that. Okay, so carrying on having a look. We're using a bucket iterator. So this is doing for us that batching similar length sequences and splitting them up into smaller ones if necessary. So this is just making sure we don't have to pad them too much, and I think this does the padding for us as well. So you remember with transformers, they don't, because they're fully parallel, they have no information about all the other inputs at each time step. So we have to give it that information about positions. So this is defining that positional encoding, and I guess this is the kind of main point here, kind of our sine and cosine on some A range. So for each 1 to n sequence, timesing it by some term and giving it position, and this will give us our curve, periodic curve over the full sequence length, defining a position in the sequence. So the transform model itself, as I make a note here, you can actually just straight up use transformer to do this entire thing for you, but it's a bit more interesting to actually look at how this works fully. So we're embedding our input vectors, our words, adding a positional encoding to them, which gives us that positional information. And we have a transformer encoder, so that's just encoding our input sequences to the same length sequence, but extracting information from the input and looking at the whole input lengths, looking where every word in it to encode it. And then for the decoder, we embed our output. So this is an embedding for the output language, our German rather than English. Oh, actually, it's German to English, so this is actually English. Another positional encoding to give us that positional information, and the decoder. So this one's auto-regressive, and so it can only look at all the words in the sentence before the current one. So this is just implemented. It's basically the same as a transformer encoder layer, but with a mask on the attention matrix. And we actually have to define this mask ourselves. So, and you can see this here. We look at the input length and make a mask, and we apply that when we apply the decoder. So that's telling it, you can only look at these as what comes beforehand. And translation. So I think, do I mention this? When it comes to translation, obviously the next word, the most likely next word, might not give the best prediction. So what we tend to do is do a beam search, where we kind of have a few different branches and pay attention and go, oh, we can branch forth. So it's a graph search to find the best translation. But in this case, we're just translating greedily for ease. We're just taking what word is the most probable next word. So it might not give the best translation, but it's much simpler to implement. And so it's basically just the same as training a classifier or generative model. We take our input sequence and our target. So we have to give it the target because we're training with teacher forcing. So we take each letter and pass it to the next one. But when we look at the output, we ignore the last one because we're predicting a following word from the end of a sentence, which we don't care about. And the target, we only look at the second word onwards. And then we're saying, just because that aligns it, so each word corresponds to the next word in the sequence. We apply our cross entropy loss to maximise the likelihood of the next word. And that does that. Let's give this a quick run. Okay, here we go, finally. Getting some first predictions here, and it's taking, obviously it takes a while to train, but not bad. We've got two individuals, we've got two who's managed to translate the correct word. Well, in some cases, but there we go. Got a little girl that's translated to a little young boy, which not too bad, and it's quite a poor translation, but yeah, I'm sure if you give that a go for a bit longer, it'll get some reasonable translations. It's quite a small network to train it a bit faster, and it'll be a bit more accurate potentially if we train on characters rather than words. But it's not a bad simple example. Yeah, thanks everyone for watching.